Hello, everyone. It's a pleasure to welcome you all to this conversation. As this is not just a technical talk, it's a glimpse into the aerospace industry's future. I'm Vyapak Tiwari, and I'm going to be your host for today's webinar, Flying into the Future with Thermoplastic Composites. Dear viewers, what we are discussing today is not just another material type existing out there. It is a material which, according to Boeing CEO Kelly Ortberg, is one of those major important technology areas that they should be investing in. Furthermore, US Senator Cantwell put it even more bluntly when she said, if we neglect thermoplastics, we could fall behind as a nation. Now, that's a very bold statement, and it reflects why thermoplastic composites are not yet just another material, but rather much more than that. Today, we are set to explore thermoplastic composites in great detail in this discussion. Joining me today are two experts, Mr. David Leach and Mr. Deepak Agrawal. Mr. Leach has over 35 years' experience in polymers, composites, and adhesives. He has been engaged in materials and process research, applications development, operations, new product introduction, and business development. Mr. Leach has held leadership roles at Cytec, Henkel, and ATC Manufacturing. He has recently founded Composite Material Solutions to share his expertise with the composites community. Mr. Leach completed his education at Imperial College London and is a fellow of SAMPI and the Institute of Materials, Minerals and Mining. Interestingly enough, he is the author or co-author of 6 book chapters and over 50 technical papers. Welcome, Mr. Leach. We are really elated to have you here with us today.
All right, thanks.
Also joining us today is Mr. Deepak Agrawal, a well known market research consultant with over 15 years of experience in the global mobility and composites industry. Holding an MBA in marketing and finance, Mr. Agrawal has led more than 200 strategic consulting projects and worked on more than 200 syndicated reports across various industries. He has worked extensively in advanced materials, especially composites and chemicals across sectors like automotive, aerospace and defense, oil and gas, construction, and recreational goods, collaborating with many leading players in aerospace and composites. Today with us, Mr. Agrawal will provide critical insights into the thermoplastics in aerospace market and will share data-driven forecast on this competitive landscape. Welcome, Mr. Agrawal. It is indeed a pleasure to have you here with us today.
Thank you, Vyapak.
So now, let's get going. To begin our conversation, I'd like to turn first to Mr. David Leach. So, David, you've had a distinguished career spanning over 3 decades at some of the most respected names in the industry, right? Cytec, Henkel, ATC Manufacturing, and your contributions have shaped key advancements across multiple domains. So, given this remarkable journey of yours, what inspired you to launch composite material solutions at this stage in your career, David?
All right, well, thanks. Yes, as you mentioned, I've had a broad range of experience. I was probably fortunate in being on what you might call the ground floor of the development of thermoplastic composites, going back over 30 years ago, and involved at that stage in some of the fundamental science, particularly around how do you combine a high viscosity thermoplastic polymer with high degrees of reinforcement, continuous reinforcement. Aspects about the polymer properties and the interfacial properties and so on. So I started out in fundamental research. As the materials were new, that led pretty quickly to working with customers and things like applications development, and particularly how do you actually make parts out of these materials, which is very different to thermosets. And then along the way into business development as well, in terms of looking at new applications and particularly what was a good fit. Along the way, I also spent some time involved with thermoset materials, everything from aircraft interiors with phenolics through structural materials with epoxies and into some high temperature materials such as benzoxazines and so on as well. So although I stepped down from full-time work with ATC Manufacturing last year, I found that there was still A lot of people in the industry wanting to move into using thermoplastic composites who did not appreciate maybe all the background, again, the high viscosity forming aspects such as using semi-crystalline polymers. And because of some of the rather stepwise advancement in thermoplastics over the years, where it's been a little sort of patchy. There's been phases where thermoplastics have had a lot of attention, and then phases where people have sort of moved away from them a bit. There's been a lot of sort of rediscovery of some things that had been really looked into in quite a lot of depth a long time ago. So part of this is really to try and help the industry advance the use of thermoplastic composites where I can with my materials and process background, particularly identifying what are some of the right processing techniques and what are some aspects of sort of design for manufacturing, and what are the types of parts and applications that work well with thermoplastics. So I felt I had something still to contribute in that. So that's why I've set up Composite Material Solutions to support the industry particularly on thermoplastics, but also on thermosets as well. I am still working with my previous company, ATC Manufacturing. I'm actually on the advisory board there. And on the thermoset side, working with Canica Aerospace as well.
Okay. Wonderful. It's great to hear that. So thank you, Mr. Leach, for that thoughtful response. It's very clear that your decision to establish composite material solutions is grounded in a deep commitment to advancing both composite technologies, right? And now, building on that perspective, I'd like to explore a more nuanced aspect of the conversation around thermoplastics, right? So, David, we often hear about the well-established advantages of thermoplastics, such as, say, for example, recyclability, faster processing, improved toughness over thermosets, right? But with your 35 plus years of experience, what would you say is the one underappreciated benefit of thermoplastics that you think doesn't receive enough attention in the aerospace discussions? Perhaps something like design flexibility, life cycle management, or even supply chain resilience. Something you believe could be a real game changer if adopted more widely.
Yeah, I think that's a good question. Actually, it might be a time to pop up that first slide if you have it as well. I think as the illustration at the top is actually from Dr. Rick Young, who is the program manager for the NASA HICAM program. And this is comparing metals with composites in general. So composites meaning generally thermoset materials right now. And as that shows, that composites certainly provide a lot of advantages. Obviously, weight is the main one that we look for in aerospace in particular. Also flexibility in design, low maintenance cost, and some other advantages, like as an example on the 787, the fact you can have higher cabin pressure. But of course, composites still tend to be somewhat more expensive in terms of acquisition cost, and also are not really suitable for very high rates. And so those are a couple of the gaps that can be particularly addressed by thermoplastics. Now, you've mentioned a few of the advantages there. Certainly in the early days of thermoplastics, toughness was one of the main drivers. And then it became particularly sort of rate and related to part cost because of the ability to fabricate thermoplastics rapidly. But I think one of the big opportunities that we'll see come through much more is the ability to use welded assembly. Now, there have been a few examples of that, particularly from GK and Fokker in the Netherlands with, first of all, the A340, then the A380 leading edges, and then more recently, the Gulfstream G650 control surfaces. But really, that's been some specific sort of one-off applications. What we're seeing is a big interest in being able to apply welding approaches more widely and in a more kind of systematic way rather than the sort of one-off solutions that have been done so far. I think also as we're moving to structural materials, you're obviously moving to unidirectional tapes, which we might talk about a little more. And welding of UD tape structures is a bit more of a challenge. So there's a lot of kind of basic science going on right now as to how to develop welding techniques. Indeed, what are the best welding techniques? But I think that's one of the big advantages that we'll see come forward that has really not been utilized fully so far. There are some other aspects that I think are underappreciated. In forming thermoplastic composite parts, you often need to use matched tooling. And not indeed often match metal tooling because of the temperatures. And so people look at that and say, oh, well, this is a very high cost of having to create these tools, machine them, or however you create them, and they have to have very high precision. But one of the things that's not appreciated is that you only need one set of tools because the parts spend such a small amount of time on the forming tools, just a few minutes, rather than many hours and days often with thermosets. And so you don't need to create rate tooling for production. Just one set of tooling is sufficient. And then I think another aspect is kind of design for manufacturing with thermoplastics that hasn't really been fully utilized yet. Although I'd say overall, there's probably the kind of synergistic benefits of all of these put together. For example, that you don't need any refrigerated storage or frozen storage. You mentioned supply chain. That fact that you don't have to refrigerate or freeze materials means you can make large batches of material. There's very little cost to store it because it can just be kept at room temperature. Also automation. Thermoplastics really lend themselves to automation very easily. The lower processing cost, which you've mentioned. Another one, when parts do need to be machined, thermoplastics tend to machine much easier than thermosets because of the higher toughness. And then also the recyclability, which is being looked at a little bit, but again, there's a lot of opportunity there where value can be gained in using thermoplastics. So there's quite a wide range of opportunities, I believe, that have not been really fully evaluated so far, where thermoplastics can really give a lot of cost, performance, and design benefits compared to current options.
Understood. All right, thank you, David, for those valuable insights. Especially the points you raised around welded assembly and the potential for significant non-recurring cost savings are particularly compelling. Turning now to a broader industry perspective, right, Mr. Leach, while the benefits of uh, thermoplastic composites in the aerospace are becoming increasingly well understood, the current economic environment presents undeniable challenges, right? So, thermoplastic composites are still frequently perceived as high cost materials, and we are seeing continued volatility in global supply chains as well. Now, even more compounded by evolving trade policies and new tariffs, right? So, taking this into context, do you believe the aerospace sector might become more cautious or hesitant in adopting thermoplastic composites? I mean, could these economic factors potentially slow the pace of their anticipated integration into the mainstream aircraft design and manufacturing?
Yeah, I think that's a good point. Obviously, some of the trade situations are a challenge because aerospace is very much an international business. As we know, for all of the major OEMs, a lot of their structures come from different places all over the world, and they have various subcontractors, tiers of manufacturing that can be broad across, particularly across North America, Europe, and Asia. So some of the things going on in trade right now certainly create some challenges there. I think there's also the broader issue that if we see a slowing of world economies in general, reduction in GDPs, at least GDP growth, then that will certainly affect the demand for new aircraft in general, because passenger air travel whether it's for leisure or business, is very closely tied to GDP growth. And also, of course, on the cargo side, if there's less trade going on, then there'll be less cargo shipments. So it may certainly slow down demand for new aircraft. Having said that, of course, certainly both Boeing and Airbus have very large backlogs right now. So there is demand even to replace the existing aircraft with more fuel-efficient ones. So that demand's not going to go away completely. But I think in implementing a technology like thermoplastics that does require some changes in manufacturing, in design, performance, and so on, one of the big aspects is having new programs come along. While thermoplastics have many attractive benefits, it's still quite hard to implement them onto existing programs because of the cost of doing requalifications. For example, you have to develop material specs and process specs and qualify materials to those, and then go through specific part qualifications. So once a program is running, it becomes very expensive in order to make any significant changes. So the best opportunities to implement thermoplastics are where we have a new program. Now that comes back, of course, to having the investment and the need to do that. And so if the major OEMs tend to see a reduction in demand for aircraft, that's going to give them less headroom to be able to start up a new program. Of course, having said that, there are some pretty big incentives, particularly in areas like fuel economy and sustainability in general, that would be very attractive to develop lower weight options, particularly to replace the current narrow body aircraft. So I think whenever those aircraft come along, there'll certainly be much more use of thermoplastics. But the current situation could lead to a delay in launch of those new aircraft, which in turn could possibly slow down thermoplastic implementation. Having said that, that's dealing more with large commercial aircraft, but there are a lot of other opportunities for thermoplastic implementation that I think we may talk about later in the presentation as well.
Okay, understood. Okay, thank you, Mr. Leach, for that response. It is clear from your response that beyond material science, strategic decisions around TPC implementation, it must also navigate market realities and long-term cost structures, right? Let's now delve a bit deeper into the materials themselves. So, within the broad category of thermoplastic composites, we encounter a diverse range of material combinations, right? Such as carbon fiber reinforced PPS, PEI, alongside glass fiber reinforced alternatives. So, based on your extensive experience, which of these material systems do you believe are best positioned for widespread adoption in aerospace over the next decade? Additionally, could you also provide some insight into the specific application area within aerospace where each of these combinations may offer the most significant advantages?
Yeah, we'll sort of do a little bit of that in combination. Some of this goes back to certainly the history of sort of adoption of thermoplastics. A lot of the early materials were things like the polyether imide or Ultem with glass fiber in the form of fabric, and particularly as organosheets. And those were really more suitable for interior applications. The polyether imide has very low flammability. And so a lot of the early applications were with glass fabric PEI, and those certainly remain. Those are ideal applications for things that are often within the fuselage or the passenger area. For things that are more external parts, more structural parts, generally you prefer to have a, semi-crystalline polymer because that gives higher resistance to a lot of the fluids that you encounter in aerospace applications, jet fuels, hydraulic fluids, cleaning materials, de-icing fluids, and so on. And so that drove an interest in PPS, polyphenylene sulfide. And that is certainly used in a number of more structural applications, although it has limitations in terms of glass transition temperature. So they tend to be secondary structure with glass fabric or carbon fabric. For much more structural applications, you really want to use unidirectional tapes and with higher temperature performance materials. So that really drove the interest in PEEK initially, and then later PEKK, and some of the other polyaryl ether ketone copolymers. There's a low temperature or low melting point, LMPAEK as it's called. And both PEKK and the low melt PEK are the ones that are certainly creating a lot more interest now.
Okay.
They do have lower process temperatures compared to PEEK, but still give the benefits of having a fairly high TG around 150 centigrade and having the very good fluid and environmental resistance. Of course, UD tapes are rather more complicated to manufacture, wetting out the polymer and getting good fiber and polymer distribution. And also in forming the parts, because with a UD tape, there's much more opportunity for the material to flow, the fibers to move around with the high viscosity polymer during forming. Of course, with a fabric material, the weave itself tends to constrain the movement of the fibers, and so they tend to be more predictable in terms of their forming behavior. But with UD tapes, there are more challenges. But certainly, the big push right now is into both larger and more structural applications, which is really driving the interest in UD tape with, as I mentioned, polymers like PEKK or the low melt PEK, and also the interest in moving to higher modulus fibers, the intermediate modulus for more structural applications. Incidentally, they do create a bit of a challenge themselves because the intermediate modulus fibers are smaller diameter. So again, wetting them out with these high viscosity thermoplastics can be a challenge, but we've seen some really very good materials now coming into the industry with again high fiber contents, which we need 60% by fiber volume, and very well wetted out, very uniform fiber matrix distribution, suitable particularly for rapid forming techniques.
Okay. Wonderful. That that really provides a very helpful view into the material landscape and where specific combinations may offer the greatest value. Building on that, I'd like to turn to the question of industry readiness, Mr. Leach. So, Mr. Leach, given your close work with aerospace OEMs and also regulatory bodies, how would you characterize their current attitude towards thermoplastic composites? You know, we know that the material qualification in aerospace is often a lengthy and rigorous process. So, are you seeing any positive developments that this may be evolving, potentially paving the way for faster acceptance and, I mean, broader adoption of the thermoplastics?
Yes, I obviously the major OEMs are already using thermoplastics in some cases, as I mentioned, sort of interiors or secondary structure, but certainly we've already seen primary structure applications with the UD tapes. And I say right now there is tremendous interest in applying thermoplastics to next generation of commercial aircraft. I think the major OEMs have really seen the benefits of thermoplastics, particularly as we've touched on the rapid forming, hence leading to lower cost finished parts, the ability to automate and recycle being some of the main drivers. And I think that has been seen to extend up to really senior levels. I think you highlighted in the introduction Kelly Ortberg recently mentioned in a US Senate hearing about how important thermoplastics are to the next generation of composite aircraft. There was also a panel session at the JEC World exhibition in France earlier this year with representatives from Boeing and Airbus, senior representatives from both companies, which both highlighted both the need and the benefits for thermoplastics. So I think in terms of commercial aircraft, that's pretty well established. Again, some of the major OEMs have at least some qualifications and specifications in place. So the sort of groundwork is set. What we're also seeing is some standardized industry specs through the NCAMP system, where materials can be qualified through the NCAMP process, and the requirements and databases become publicly available, so that a wider range of companies can use both the design data and the related process specs. If you went back a year or two ago, there were probably only about a couple of thermoplastic composites with NCAMP databases, but already there are many more and quite a lot in the works. And that really opens up the opportunity to apply thermoplastics through many more opportunities. Other companies outside of what you consider the traditional OEMs, perhaps Boeing, Airbus, and one or two others. So, for instance, the advanced air mobility or eVTOL applications, where you have a lot of new players coming in who don't have historic databases, and they can leverage the NCAMP databases. Also drones, particularly anywhere where you're going to be manufacturing parts in relatively high volumes, which obviously advanced air mobility and unmanned vehicles of all types, like everything from commercial drones, cargo or delivery drones, ones for emergency services, as well as defense. So the fact that we now have a situation where the use of thermoplastics can be much more sort of democratized through these standard and industry available specifications is really opening up a lot more applications, and in some cases quite quickly as well.
Understood. Also, on a related note, Mr. Leach, while thermoplastic composites are currently used primarily in smaller components, right, such as clips and brackets, the broader goal is is clearly to scale their application. So, in your view, what might we begin? When might we begin to see a meaningful shift towards the use of thermoplastic composites in larger structural aerospace components? And what are the key challenges that must be addressed to make this transition possible?
Yeah, sure. Maybe if we could pull up the slides again. Actually,
Yeah.
slide 5 is a good example, if we can move to that. There's obviously a great deal of interest in moving to larger structures. As you mentioned, a lot of the parts that have been manufactured so far, whether it is in fabric, reinforcement, or unidirectional tapes, are relatively small, things that are sort of smaller than about a meter or so in size. But there's tremendous interest in moving to much larger structure, where indeed the benefits may actually be much more once you sort of overcome the technology hurdles of having to use different techniques to thermosets. So there's been a number of large-scale demonstrators built. In the upper left there, one that's been very widely publicized, of course, is the multifunctional fuselage demonstrator from the European consortium, partially funded through the European Clean Sky program, involving a lot of partners, including Airbus, DLR and NLR, the German and Dutch National Aerospace Institutes, GK and Fokker, and a wide range of other companies. And the multifunctional fuselage demonstrator has been very interesting, not only in manufacturing the structure, but also evaluating different manufacturing and assembly techniques, and also how features and systems can be integrated into the structure rather than having them as separate events, if you like, within the aircraft. So that's one large demonstrator. I think kind of sets a little bit of the path as to where things are going. Oh, sorry, if we just flip back to the previous one. I think fuselage structure in general is one of the areas that has been tremendously of interest. A number of others on the slide. On the right-hand side here, we've seen several companies and consortia doing fuselage demonstrators, which have a really interesting combination of a large area skin, often variable thickness, some sort of frames, and then also stringers or stiffeners, and then assembling all of those together. Again, welding being one of the big opportunities. So we've seen demonstrators from a consortium led by Spirit Aerosystems. There was a demonstrator from Korean Aerospace that was shown at JEC last year. In fact, Spirit also was up for Innovation Award at JEC last year. The Hyperpass Consortium in France doing a similar thing. And then also this year, Kawasaki Heavy Industries, KHI, demonstrated a fuselage section. And all of these have various different approaches as to how you make the skins, the frames, the stiffeners. I'd also highlight Collins Aerospace, although this is a nacelle application. But again, nacelles can get quite large and in many ways have similar structures. So they are also moving down this path themselves in terms of being able to build these large kind of stiffened skin structures. Yeah, if we do maybe move on to the next slide as well, as you did. I think some of the other things that we see going on, we mentioned the Clean Sky multifunctional fuselage demonstrator, which again has built a full barrel section on the upper right there. In the USA, the NASA-led high-rate composites manufacturing program, or HICAM, it's going to be building some full-scale demonstrators. Kind of that shows a illustration of the fuselage section that they're looking to do, which could be a combination actually of thermoset and thermoplastic. And that's also intended to reach high manufacturing readiness levels, MRLs, so that it would develop technologies that are truly production ready beyond being just simply a demonstrator. I think we also see there's been significant commitment and investment. Of course, as recently publicized, Airbus has installed a 5 meter by 2 meter large forming press at their Bremen facility, which is a pretty large commitment to advances in thermoplastic forming. And then we've got a couple of other kind of development consortia. Of course, the Thermoplastic Composites Research Center in the Netherlands has been working on kind of low to medium TRL research for many years, going back about 15 years. So really developing some of the fundamental science that's based in Enschede in eastern Netherlands on the University of Twente campus, with many partners both in aerospace and automotive, material suppliers and fabricators as well. And then more recently, the American Aerospace Materials Manufacturing Center, or AAMMC, received funding through the US government to create a tech hub to advance large-scale manufacturing of thermoplastic structures to, again, full production readiness levels, in fact, to very high MRL levels. And that is a consortium with many members, but just to highlight a few of the ones involved with aerospace, it includes Boeing, Collins, Spirit Aerosystems, ATC Manufacturing, and some of the material suppliers like ScienceCo and Toray. So that will be installing equipment to make very large-scale thermoplastic composite parts, and again, advance the process technologies to full production readiness. So I think we see there's really a tremendous amount going on in the industry right now to enable thermoplastic composite fabrication to be ready for that next generation of aircraft and large-scale structures when they come along in the next few years.
Thank you. Thank you, Mr. Leach. Surely these lay a strong foundation for understanding both the technical potential and the adoption landscape of the thermoplastic composites in the aerospace. Right. Now, to complement that with the view of a market focused lens, I'd like to turn my attention to Mr. Deepak Agrawal now. Mr. Agrawal, since you have been first handedly associated with the research in this space, let's hear your perspective on the trajectory of thermoplastics in the aerospace industry. Can you please take us through the past, present, and the future of thermoplastic composites in the aerospace market, in terms of numbers?
Yeah. So, as you know, just to add a few points, what David already commented on that. So, when you say that thermoplastic composites is very uniquely presented in the entire composite value chain. So, if we talk about the overall opportunities, the opportunities are very huge. Currently, as even David mentioned, that a lot of parts being manufactured, which are smaller in size, but gradually we think that as a lot of already R&Ds are going on, which actually helping the industry stakeholders to understand the potential of thermoplastic composite in large components. So let's discuss some market numbers one by one. So Vyapa, can you please share the
Yeah.
screen?
Yeah, sure.
Yeah. So basically, I'm trying to show a lens, where exactly currently, a thermoplastic composite positioned in the overall composite market. So if you look at the overall composite materials, it's around 36 billion pound in 2024. And out of that, if you talk about aerospace and defense, which is extremely niche market category, having a market of around 115 million LBS. So if you look at that, it's hardly 0.3%.
Okay.
Out of that aerospace and defense composite materials market, around 2.2 million LBS is thermoplastic composites, so which is hardly 2%. But the market is, as I mentioned, that the market is very uniquely positioned. So if you look at the overall market, we are anticipating the market is currently around 393 million US dollars, representing a volume of around 2.2 million LBS. But look at the growth trajectories; it's likely to grow around 11% in next 7 years, ultimately reaching a market value of around 900 million US dollars with a volume data of around 4.7 million LBS. And if we talk about the overall thermoset composite growth in aerospace and defense, and if we talk about the overall aerospace and defense thermoplastic composite growth. So the thermoplastic is growing around 2x than the overall thermoset growth in aerospace and defense. That shows the potential that the material holds, and that's the reason there has been a lot of discussion about this material, driven by its numerous advantages, including sustainability. So let's try to understand, where exactly this material, is positioned and where exactly it is being used, what are the applications, which forms, and how this material is being consolidated in other regions. So in terms of aircraft type, commercial aircraft is the biggest user. If you talk about again in aircraft categories like Airbus 350 and Boeing 787 are the major ones, they have been using a lot of clip and cleats. So I think in Airbus 350 there are around 8,000 clip and cleats made from composites. In case of Boeing 787, it's around 10,000 to 15,000 units. again made of the thermoplastic composites. That makes the commercial aircraft being the biggest market category with around 85% share in terms of both, whether you talk about value and whether you talk about volume. Among material, it's very unique. If you talk about PPS and peak, if we add this together, that's become around 85% market. But if you talk about volume basis, reason being that the cost of PPS is much lower than peak, it's the dominance of PPS is much higher at around 65%. Among applications, airframe, we basically count assembly components under the airframe. Somebody counts it under the head of interiors, but in airframe, it's around the biggest category, around 63% share in terms of volume, around 67% in terms of value. In terms of fiber type, carbon fiber is a major category in terms of value, having around 90% share. And in terms of consolidation type, press molding is the biggest category, having around 85% share. Now let's discuss more about PPS, peak, and PEI, since this is the most used resin systems in thermoplastic composites. So when you say PPS, as I mentioned, that is dominant in terms of volume. If you talk about in terms of value, it is more about peak. So if you see that by 2031, out of the 900 million market of aerospace and defense thermoplastic composites, we believe that around 50% would be peak-based thermoplastic composites and around 40% would be around PPS-based. The reason being that both resin system, whether you talk about PPS or peak, both are used preferably reinforced with carbon fiber for manufacturing parts like clips, clits, or and gradually there would be a lot of bigger applications that may be fuselage and other ones. Again, the resin system would be the remain one, whether it would be peak or PPS based. PEI is more preferred in interiors, reason being that it has a really good FST property, and that makes one of the ideal material for interior applications. Now, moving down to next slide, we mapped what are the platforms currently where thermoplastic composites are used. So if we talk about carbon fiber PPS, there are a lot of applications being manufactured, like that may be ribs or angle brackets, clips or brackets for rudders, elevators, fuselage clips and clits, fuselage panel skins, horizontal tail planes, shear wraps, and engine pylon covers. Again, the kind of platforms where such kind of applications are used is the Airbus 350, Airbus 380, Airbus 340, Boeing 787, AW169, and Gulfstream 650 and Dassault F5X. So that if you talk about other applications, again made from different materials, whether it is a carbon fiber PEEK, carbon fiber PEI, or glass fiber PPS. So again, that gives a very clear idea that Airbus is far ahead in terms of usage of thermoplastic composites. Then Boeing, reason being that if you look at all the major applications, all the major platforms, whether it is the Airbus 350 or maybe other ones having greater amount of thermoplastic composites than that of Boeing ones. Just one more slide. The same thing we have done it for by airframe and interiors. So that clearly says that if you talk about airframe, majority of airframe applications, whether it is a clits or maybe fixed wing leading edge or maybe ribs or movable spars, so all are creating a greater opportunity for thermoplastic composites. If you look at the 900 million again, 600, which is equivalent to 66%, would be coming from airframe. Interiors again is going to be really good applications, having around 232 million US dollar market opportunity. So that gives a very clear idea that the growth in near term is really impressive. So we anticipate around 11% CAGR in next 5 years or next 6 years, and that tells that how lucrative this market is in terms of attractiveness, in terms of investment, or in terms of R&D.
Thank you, Mr. Agrawal. Thank you so much for that insightful and data rich overview. Your perspective on the market dynamics provided a critical context for today's discussion. Now, As we move forward to the final question of today's webinar, I'd like to turn to Mr. David Leach again. Mr. Leach, talking of eVTOLs, we've already talked of eVTOLs briefly here. So, talking of eVTOLs today, over 90% of the eVTOL OEMs rely on thermoset composites, right? However, thermoplastics offer compelling advantages we've already seen. So, given the industry's scaling challenges, how soon do you foresee a viable transition to thermoplastic composites? And what key breakthroughs are needed to accelerate this shift?
Right. I think inevitably with the sort of advanced air mobility VTOL applications, there's been a race to get vehicles in the air and get them certified. And so the tendency has been to use readily available materials and processes, um, and particularly ones that can be prototyped quickly. As an example, thermoset technologies are obviously very well established, and you can often use low-cost tooling for prototyping. So kind of if you're making design changes and so on, that's very easy to incorporate. So I think it's inevitable that the initial vehicles have used thermoset materials. I think it's a given that these have to be very lightweight and so will be composite intensive. But of course, as we move to higher rates, and certainly the discussions are around, building 1,000 or more of these a year, then you need composite systems that can be fabricated both quickly and at lower cost, and ideally with a high degree of automation. So thermoplastics is obviously a very good fit. I think we started to see a bit of a trend that way already for certainly the sort of, if you like, the next generation or full production phase. It was announced publicly a year or two ago that Joby was working with GKN Fokker on thermoplastic composite control surfaces. Also, some companies in the eVTOL space are certainly taking a bit of a longer term view. Again, Supernal, which is wholly owned by Hyundai, is more looking at about a 2028 production readiness. And again, it's been reported in the industry that they're also much of their structure of their aircraft is built by GKN Fokker. Again, GKN makes metallic thermoset and thermoplastic parts, but of course what they're particularly known for is thermoplastics. So I think we can probably infer from that there is a lot going on for production rate manufacture of the eVTOLs in thermoplastics. I will say though, it's not just a case of taking maybe a thermoset part and saying, okay, we're going to go make this in thermoplastic and we'll make it faster and cheaper. You really need to think about thermoplastic forming from the beginning. As Deepak mentioned, the majority of parts are manufactured using stamp forming or rapid forming techniques. I think he said 85%. And those are very cost effective in thermoplastics, but because you're moving the material, forming the part very quickly, you have to take that into consideration in terms of the design for manufacturing. So it's often not just a case of taking a thermoset design part and translating that directly into thermoplastics. You often have to think about some of the design aspects that come into that. I think the welded assembly that we mentioned will be important as well. Actually, my friend Dave Huber, I saw Huber in the chat mentioned out of autoclave, which is certainly a good opportunity with thermoplastics where we have very well impregnated materials. Again, there can be quite a strong interaction between the materials, the processing, and the parts with thermoplastics that needs to be appreciated. I think, as we said, a lot of medium-sized parts, things like control surfaces, doors, a lot of the structure of AAM, of course, is not as large as commercial aircraft. So there's there's a tremendous amount of opportunity. Another one that's really being looked at is blades, and I think at Stratview there you had a recent webinar as well on blades. Of course, for any of the eVTOLs, there'll be a large number of blades required and probably replaced as well. Although those are fairly complex parts to make, they're not just a single sort of monolithic structure. Most blades use some sort of core, be it foam or honeycomb, the way they're designed now, and also have to be tapered both across the core, down the length, and also have to have extremely precise dimensional requirements to create the lift that's expected consistently. So I think blades could be a good opportunity, but I think there are some challenges as to how to manufacture those. But I think the sheer volume of blades that will be needed will drive a lot of interest in using those sorts of techniques. And I think automation is really going to be a key to a lot of these, which again, thermoplastics can lend themselves to, as you're not worrying about things like tack and out time. So you can really highly automate the processes, both for assembling the plies, consolidating them, and forming them into the finished part. So I think certainly eVTOLs will be a big breakthrough opportunity for thermoplastics in the next few years.
Okay, thank you, Mr. Leach, for that thoughtful response on the future of thermoplastics in the eVTOL sector. Mr. Leach, we are live on LinkedIn right now, and we have some questions, some interesting questions from our viewers live. So Suresh Mishra asks, I have questions. We have current setup autoclave with 250 degrees Celsius and 10 bar pressure. Is this equipment enough to start the thermoplastic composite product manufacturing?
Yeah, that's a good question. If we're talking about aerospace, you're generally talking about a bit higher temperature requirements for the polymers we've been discussing. Even PEI and PPS are over 300 centigrade forming temperature typically, although PEI can be formed a little lower. If you're getting up into even the low melt PEK, PEC, and peak, you're talking more about temperatures in the sort of 340 to 380 centigrade forming temperature required. Certainly those semi-crystalline polymers in the aerolithic ketone family, all the melt temperatures are over 300 centigrade. But if we're talking about non-aerospace, then maybe things like nylons or PET, then 250 centigrade would be sufficient. And 10 bar is certainly more than enough pressure. As we mentioned, in some cases, you can use even vacuum pressure only.
Okay, wonderful. We'll move to the next question. Will thermoplastic composite prepeg be widely used in the drone applications?
I would almost certainly say yes. Again, drones, we mentioned there's quite a wide range of different possibilities there, whether they're for delivery, surveillance,
सर इसका पढ़े हुए
mapping, emergency services, defense, and so obviously, they will be made in quite large quantities as well, which again really lends itself to the high rate possibilities with thermoplastics. Of course, drones tend to be smaller structures, so you have to consider some of those designed for manufacturing aspects, particularly if you want variable thickness parts or tight radii parts, which sometimes can be a challenge in thermoplastics. But overall, yeah, I think there'll be a very wide use in drones.
Okay. Now, Molishwar is asking, what is the potential of nylon 6 as matrix for FRP compared to other existing thermoplastic polymers?
Again, if we're talking about aerospace, you usually need higher temperature performance, even for things inside the fuselage barrel, inside the pressurized area. But if we're looking at maybe some of the things like drones that are maybe only going to be subject to typical sort of ambient temperatures, so maybe things that are more like going from cold temperatures, maybe it's like -20 up to maybe +50 centigrade or so, then I think nylons have a lot of application. Also automotive, of course, we're seeing a lot of lightweighting going on in automotive, particularly with the move to electric vehicles. Both the structure itself and battery boxes, battery compartments, and so on. So I think that's an opportunity for the future with nylons or PET materials.
All right. We'll just take one more question. It's a comprehensive question asked by Laurie. All right. I'm reading it out. Hi, David. I'm exploring the potential for using injection molding technology in the aviation sector and would appreciate your insight. From your experience, which types of parts can be effectively produced for aviation using injection molding equipment? What would you identify as the main strength and limitations of this method in that context? Also, based on current trend and manufacturing standards in the industry, what next steps or complementary manufacturing methods would you recommend for a business aiming to invest in aviation parts production? Thanks in advance for your time,
All
Laurie.
right. Okay, pretty wide-ranging question there. Of course, a lot of what we've been talking about has been continuous fiber, highly reinforced materials. If we're looking at injection molding, then you're generally talking about materials with maybe more like 20 to 40% reinforcement by weight, that is, and very short fibers. So, of course, the advantage of injection molding is being able to make very complex parts, much more so than you can do with continuous materials. But of course, you don't get the same performance in a short fiber material as you do in a highly reinforced continuous fiber material. So I would say a lot of the applications for injection molding are often more in the interior applications. And although that also, of course, drives flammability requirements, so you need to use polymers with very good flammability resistance. Again, we mentioned things like PEI and PPS in that context as well. That would tend to also drive you to kind of smaller or more moderate-sized parts compared to continuous fiber. And actually, I was just going to mention, I see there's just a comment in the chat about overmolding. That was actually something I was going to mention, because one of the opportunities that has been demonstrated with a number of organizations, including TPRC, is the use of overmolding, where you can take a continuous fiber reinforced part and overmold it with a short fiber material to add in a lot more detail, like stiffening elements or attachment points or reinforcement points around the edge. For instance, access doors is a good example, smaller access doors where you can do that. Or indeed, make a much kind of stiffer component that might have been an injection molded component originally, but using a continuous fiber insert increase the stiffness considerably. So I think there are good opportunities there. There are quite a lot of smaller kind of injection molded parts, also in terms of electronic parts on aircraft, which of course are more and more important as well these days. So I think there's opportunities there, but it's not going to be the major structure, because that's going to be really in continuous fiber reinforcement in order to get the weight and performance that's needed.
Okay, voice is not
All right,
coming there.
David. Yeah, David, we have a few more questions on LinkedIn live chat. So if your time allows, we can take them.
Yeah, sure. I can take a few more. Yeah.
Okay, so Suresh again asks, do we need similar vacuum bag technologies we are following for thermoset composite?
Well, you can generally, if you're going to do something that's sort of out of autoclave, like oven consolidation, then using traditional technologies, bagging is an option. Although, of course, we mentioned the high temperatures, you're over 300 centigrade. So you generally need to use more expensive and specialist bagging materials. Like you often need to use polyimide type films and higher temperature sealant tapes and so on. So it is more expensive, more specialized than doing thermosets. Also, in general, with thermoplastics, you want to try and avoid having to use bags if you can, because obviously those are one-time use kind of throwaway consumable materials. But it can make sense in certain applications, like if you maybe is doing a large skin, you might do just as an example, a high rate laydown with a AFP type equipment. So you're not worried about getting full consolidation, just really getting all the plies tacked together. And then bag that and put it in an oven to get full consolidation on the skin. For a large area part, that could make sense to bag it up. But typically for kind of smaller or medium-sized parts, you're going to want to use a more rapid forming, like a stamp forming type technique.
All right. Suresh has another question. This would be the last question we'll be taking. Thermoplastic composite processing will follow open molding, layup and bagging, or closed mold technology?
Yeah, in most cases, it's closed molding. Again, it relates a little bit back to the previous question. Certainly, you can lay materials up, although the flip side of not having the tack is you have to use some technique, often thermal or ultrasonic tacking for the plies to stay in place, and then bag that up and consolidate it. But just to relate to the previous question, for large area skins, you might use a single-sided tool and bag a layup or a partially consolidated layup onto that. But in most cases, you're going to be using a matched metal tool in order to form the part, both the inner and outer mold lines of the part simultaneously.
All right. Thank you. Thank you so much for this, David, for taking the questions live. Must have been really very helpful for the audience. Now, with that, I would like to extend my sincere thanks to both Mr. David Leach and Mr. Deepak Agrawal for sharing their time, expertise, and perspectives with us today. Your contributions have made this session truly insightful and valuable. Thank you, Mr. Leach. Thank you, Mr. Agrawal.
All right, thanks for the opportunity. And if people who are on the webinar want to reach out to me, they can contact me through LinkedIn, of course.
Thank you.
Yes. And to our audience, thank you for joining us and for your engagement throughout the webinar. But before we conclude, I'm pleased to share that our next session will take place on 2nd of May with Dr. Mansoor Chelebi with a focused discussion on the eVTOL market and the technologies shaping its future. We hope to see you there. Lastly, don't forget to follow and subscribe to our social media channels as we are committed to bringing you more of these expert led sessions on critical topics in aerospace, advanced materials, and mobility. Thank you once again, and we look forward to welcoming you at our next webinar. Goodbye. Take care, everyone. Thank you, David. Thank you,
Thank you.
Deepak.
Thanks. Yeah. Bye.
Bye.